All right, so we're going to continue talking about sampling today. The story I want you to think about. Suppose the Tricolor Times, that's our school paper, reports that out of the 330 students asked, 144 said they like eating the school lunch that's here. So this is a proportion problem. So thinking 144 out of 330, that's 0.436 or 43.6%. So then my question becomes, does this mean that 43.6% of all students at Granger High School like the school lunch? Well, hopefully in your brain you're thinking, no, of course not. It's a sample. Okay, 43.6% came from a sample, and we expect our sample to give us the wrong number. We expect that. It's not going to be perfect. There's no way. Now, hopefully it's close. Right? Hopefully we're close to the right answer, but it's not going to be perfect. So we call this number here p hat. P hat. It's the proportion of students that like school lunch, but we put the hat on it because it's based on a sample. So please make sure you remember the difference between p and p hat. This one is the truth. This one is our statistic. It's a guess based on a sample. So we're guessing that 43.6% of all, notice all Granger High School students like the school lunch. But that's probably not the truth. So then the question becomes, well, how are we going to find the truth? P hat, that's easy. I just go out and ask people. But what does that tell me about truly what proportion of students like the school lunch? So from Chapter 18, hopefully you recall that we could create a normal model for proportion using p, the true proportion, as our center, and calculate the standard deviation pq over n square root. Unfortunately, we don't know p. I don't know what this is. I don't know the truth. I only know my statistic. So instead of using the truth, we are going to just make a guess. Instead of p, we're just going to use p hat. That's the closest thing we have. So instead of p, we'll use p hat, and instead of q, we'll use q hat. All right, so if we go ahead and figure that out, it means we're going to be using a normal model with 0.436 in the center. And our standard deviation will be 0.436 times 0.564 over 330. That's how many I said I asked, which is approximately 0.027 as our standard deviation. So I can go ahead and set up my normal model this way. Same thing we were talking about in Chapter 18, so I actually went ahead and did that. So you can see my 0.436 in the middle, and I went out my 1, 2, 3 standard deviations on either side. So the question becomes, well, how does that help us? How does that help us? Well, remember, 95% is going to be kind of our just standard. I can be pretty sure that p is somewhere in there. What? Remember in Chapter 18, we draw a normal model, we put p in the middle, and if we went out 2 standard deviations on either side, we'd say, well, 95% of p hat, right, of sample proportions would be in that range. So it kind of makes sense. We're kind of just going backwards. We're saying, well, I am putting p hat in the middle, and then I'm pretty sure if I go out 1 and 2, that I'll capture the real p in there somewhere. Okay, so I'm kind of doing almost a working backwards idea. So I'm pretty sure p is going to be somewhere between 38.2% and 49%. All right, so what exactly does this mean that I'm saying between 38.2% and 49%? What is that? Well, does it mean that 43.6% of all Granger students like school lunch? No, we said that. We expect variation when we sample. This was our p hat, and it's probably wrong. It probably didn't give us the exact value of p, the true proportion. Okay, so maybe it means this. It is probably true that 43.6% of Granger High School students like the school lunch. Again, it's probably not true. The true proportion is, it's just really unlikely that we nailed it right on in our one sample. All right. How about we don't know exactly what proportion of Granger High School students like school lunch. That's true. I do not know what the true proportion is, but I know it's between 38.2% and 49%. All right, that's the numbers I got here. Well, unfortunately, this sounds just a little bit too certain. I don't know that it's between those numbers. I think it is. I'm pretty sure, but it might not be exactly. We don't know for certain. We can never be positive the value for p, our true proportion, is in our interval. Okay, interval. Yeah, remember I gave that range of numbers? It's somewhere between 38.2 and, excuse me, don't need a decimal there, and 49%. We put little numbers around that, and this is just a mathematical notation for interval. It means it's somewhere in there. I'm giving you the endpoints. Okay, well, let's try another way of thinking of this. We don't know exactly what proportion of Granger High School students like school lunch, but the interval from 38.2% to 49% probably contains the true proportion. As a matter of fact, this is right. This is what I'm doing. I don't know what the truth is. I don't know p. Like I don't know. But I'm making a guess. I made my guess based upon this normal model and what I know about sampling distributions. So I just kind of reached out 2 standard deviations in either direction. And there's no guarantee that the true proportion is in there, but I'm pretty sure. I'm pretty sure. Right? 95% of it, right? 95%, that's almost everything. Okay, so what I said is this actually sounds kind of lame. It makes a lot of sense, but we're going to just fancy it up just a little bit. We're going to say it this way. We are 95% confident. Where did 95% come from? That was I went up and down 2 standard deviations. We're 95% confident that between 38.2% and 49%, it's my interval, right? My interval of Granger High School students like the school lunch. Okay. So I do this, I'm 95% confident. That's the same as this probably. Just sounds a little more technical. We will actually be talking about this phrase a little more in depth in class, so we can see a visual to help us understand why I use that phrase.